Welcome everyone to our video on solubility equilibrium. In this video, we will review the dissociation of ionic compounds in water. We will define molar solubility. That will lead us to define solubility equilibrium and learn how to write the KSP equation. And finally, we will practice a solubility equilibrium question by solving for KSP given the molar solubility. Recall from previous courses that when an ionic compound dissolves in water, they split into two ions. For example, sodium chloride breaks up into one sodium ion and one chloride ion. We can write this as a chemical equation with the solid ionic compound on the left and the dissociated aqueous ions on the right. We have to look at the nomenclature of the ionic compound to tell us what the mole ratio will be of the dissociated ions. In every 1 magnesium chloride, there is 1 magnesium ion and 2 chloride ions. So when it dissociates, we get a 1 to 1 to 2 ratio. Recall that polyatomic ions will be treated exactly the same way. They'll always dissociate into one cation and one anion, with any sort of coefficient related to the nomenclature of the ionic compound. In 1 potassium permanganate, there's 1 potassium ion and 1 permanganate ion. It's also helpful to have a picture in your mind of what this is going to look like on the particle level. When we have a solid ionic compound, those ions are held tightly together in a regular lattice by electrostatic forces of attraction. When we dissolve that ionic compound in water, those ions dissociate and are held apart by new forces of attraction with the water molecules. They are hydrated. When we draw a particle diagram of aqueous ions, we omit the water because we want to focus on the dissociated ions. In previous courses, you've also learned about solubility rules. You learned about the solubility rules in a qualitative way, where we classified ionic compounds as having high solubility or low solubility. In this chart, it uses the term very soluble and slightly soluble, which means the same thing. A very soluble compound will dissolve well. More than 0.1 moles can be dissolved in a liter. A slightly soluble ionic compound will be one that very little dissolves. It would be an ionic compound where if you took a small amount and tried to dissolve it in a given amount of water, some of it would likely stay undissolved. We talked about the solubility rules in past courses in the context of predicting whether a precipitate would form from a double displacement reaction. Recall that all group 1 metals that are involved in ionic compounds are always highly soluble. All nitrates are highly soluble, and as well as all ammonium compounds. When we use the term solubility, we're defining a specific amount of the solute which can be dissolved in a given volume of water. When you've reached the solubility point for an ionic compound, that is by definition a saturated solution. You cannot dissolve any more of that ionic compound in that volume of water. Solubility curves of ionic compounds tell us the precise mass of an ionic compound that can be dissolved in a given volume of water at a specific temperature. As you can see by the curve here, for most ionic compounds, their solubility increases as we increase temperature, but that does not need to be the case. The lines on this curve here represents the saturation point for each of these ionic compounds. So if we want to know how much of an ionic compound we can dissolve in a given volume of water at a given temperature, we just follow the curve. For example, at 30 degrees, approximately 45 grams of potassium nitrate can be dissolved in 100 grams of water. We've already mentioned the idea of a saturated solution, and if we have a solution which does not have the maximum amount of solute dissolved at that given temperature, we call that an unsaturated solution. More of the solute can still be dissolved at that given temperature. And finally, Solubility refers to a concentration. Specifically, the solubility of an ionic compound refers to the concentration of that ionic compound in a saturated solution. This leads us now to solubility equilibrium. When we dissolve or try to dissolve an ionic compound with fairly low solubility, we notice that not all of the ionic compound dissolves. So what we have there is an incomplete reaction. We still have some of the reactant, the undissolved ionic compound, but some of the ionic compound did dissociate and dissolve into the water. We also know that the dissolving process is a reversible reaction. How do we know that? Well, a precipitation reaction is just the reverse of the dissolving reaction. Precipitation of an ionic compound is the ionic compound coming out of solution and forming a solid again. We see some of our conditions for chemical equilibrium here, and it turns out that when we have a saturated solution of an ionic compound in a closed system, we have an equilibrium system. Here's the equilibrium equation for a low solubility salt, lead 2 chloride. On the left-hand side, we have the solid ionic compound. On the right-hand side, we have the dissociated ions. The forward reaction represents the dissolving process. The reverse reaction represents the precipitation process. We know that equilibrium systems follow the equilibrium law. And so if we have an equilibrium system, we can write an equilibrium law expression. For this specific reaction here, the dissolving of an ionic compound, the equilibrium expression is a product of the ion concentrations raised to their molar coefficients in a saturated solution. It's called the solubility product constant because this equation for a solubility equilibrium is always just a product. There's no denominator. That's because the left side of the equation, which is usually found as the denominator in the equilibrium law expression, is a solid. And we know that solids, because they are pure substances, do not appear on the right-hand side of an equilibrium law expression. We will be focusing on ionic compounds which have low solubility. That's because under normal conditions, we have the conditions for chemical equilibrium, an incomplete reaction because not all of them dissolve. Ionic compounds with high solubility dissolve completely. So as a result, the equilibrium essentially lies entirely on the right-hand side under most normal conditions. So we will not be looking at the equilibrium systems involving highly soluble ionic compounds. The KSP equation involves ion concentrations. Specifically, those are ion amount concentrations measured in moles per liter in a saturated solution. That's because a saturated solution, by definition, is at equilibrium. So the concentrations we are substituting into the KSP equation, as always, are equilibrium concentrations. We get those concentrations from knowing the molar solubility of an ionic compound. The molar solubility of an ionic compound is the amount of moles of the solute which can be dissolved in 1 liter of water. Before going through an example, let's remind ourselves of some key points about the KSP equation. Solubility equilibrium refers to a single type of equilibrium system. An equilibrium system where the left-hand side is the solid ionic compound, and that's an equilibrium with 2 ions, the cation and the anion from that ionic compound. The KSP equation, or the KSP expression, is always an ion product of the ion concentrations at equilibrium, or in a saturated solution, raised to the powers of their molar coefficients. Let's now look at an example of how we use the KSP expression. Let's try this example here. Let's find the KSP of lead 2 iodide if 1.29 times 10 to the negative 3 moles can be dissolved in 1 liter of water to make a saturated solution. Before getting into the question, we're always going to need our solubility equation or our solubility reaction. So let's start off by writing that. So here's our equilibrium expression, the solid ionic compound on the left, the dissociated ions on the right. Let's now build an ice table as we do with most equilibrium problems. The question tells us that 1.29 times 10 to the negative 3 moles of that solute can be dissolved in 1 liter of water. So here, as my initial concentration, we will write 1.29 times 10 to the negative 3 moles per liter. And even though solids don't have concentrations, I like to put that there as the initial concentration to imagine taking that ionic compound and dissolving it in water. For every 1 mole of lead 2 iodide which dissolves, we'll produce 1 mole of lead ions. So if we dissolve 1.29 times 10 to the negative 3 moles of lead iodide in a liter of water, that will produce 1.29 times 10 to the negative 3 moles per liter of lead ions. There's a 1 to 2 ratio between the ionic compound and the iodide. So I'll multiply the moles that were dissolved in a liter of water by 2 to get the concentration that's going to dissolve of my iodide ions. Since in this case we were just dissolving in water and there were no ion concentrations initially, our equilibrium concentrations will equal to the change. So if I dissolve 1.29 times 10 to the negative 3 moles of lead iodide in a liter of water, that will get me a saturated solution, which by definition is my equilibrium situation. And the equilibrium concentrations of the ions will be 1.29 times 10 to the negative 3 moles in a liter of water for the lead ions, and twice that, 2.58 times 10 to the negative 3 moles per liter of the iodide ions. Let's now bring in the KSP expression. Our KSP expression is always the product of the equilibrium concentrations of the ions raised to their molar coefficient in the balanced chemical equation. In this case, lead ion concentration multiplied by the iodide concentration squared. All that's left to do now is to substitute in our equilibrium concentrations and solve for the KSP value. So the KSP value for lead iodide is 8.59 times 10 to the negative 9. As with previous equilibrium constants, we will leave this as dimensionless without any units. And we should note something about the magnitude of that equilibrium constant. Recall that the magnitude, the size of that equilibrium constant, tells us something about where the equilibrium position lies, whether it lies further to the right or further to the left. This very small value came from 2 very small concentrations. This very small value, much less than 1, tells us that the equilibrium system lies heavily to the left-hand side. Very few ions will dissolve when placed in water.